Okay, this is for Physics 5B Sacramento State. It's July 12th, 2020, and this is the beginning of Chapter 19, which starts off talking about basically a comparison between what you would have studied in Physics 5A with gravitational force and trying to compare it to what we're running into now with these electric fields and the electric force. So back then, you've got this gravitational force acting on a mass, okay? And so the mass feels a force, and then the gravitational field, the gravitational force does work on the mass. Remember, work equals force times distance over which that force is applied. Well, we got the same sort of thing going on here. Instead of a gravitational field, we have an electric field. Instead of a gravitational force, we have an electric force on a charged object. Okay, so you got some positive charged object in there. The electric field lines go away from the positive up here down towards the negative down here. So obviously the charged object will be repelled by the positives and go down towards the negatives. The gravitational force does work on the mass, causing it to accelerate and converting potential energy into kinetic energy. In the same way, the electric force does work on a charged particle, causing it to accelerate and converting potential energy into kinetic energy. So this guy has potential energy here because it's going to be a force acting on moving it this way, okay? Just like this mass has got potential energy because the gravitational force is going to act on it and pull it down until it hits the ground. Okay, just as with mechanics, work is equal to force applied times the distance over which that force is applied. Work equals the force on our charged particle times the distance over which that force is applied. From chapter 18, we have this equation. Remember, we have chapter 18 here. We've got the this equation here. Force equals charge times the electric field. So we also have force equals charge times the electric field. Remember that the electric field in this case is newtons per coulomb. How many forces of newtons do we have per 1 coulomb? Basically is what it's telling you. It's 25 newtons per coulomb. That means every 1 coulomb we stick in there is going to feel 25 newtons of force. Okay? So now if I plug in for force equals QE, we get work equals QED. I'm just plugging this in, this guy in, to FE. So this guy replaced FE in this equation. So now we've got this equation. Work equals the charge times the electric field times the distance that the work was done. But we also know from the good old days of Physics 5A that work is equal to the change in potential energy. Okay, so you go from the potential energy decreases, right? So you want the work to be positive, so you put a negative sign up there because the final potential energy is less than the initial potential energy. When you drop a ball, its initial potential energy is greater than its final kinetic potential energy, but it's final minus initial. So you get rid of that minus sign, you stick a negative out front. So in this case, we got the potential energy at point B minus the potential energy at point A. That's going to be a negative number, but we put the negative out front so we get a positive work. So QED right here replaces the work. That's going to equal the change in potential energy equals the change in potential energy, and so on. Okay. So also we know that from last semester or 5A that the work done is equal to the change in the potential energy. At this point, it's a good idea to introduce voltage. Voltage is related to energy. A change in voltage is equal to the change in potential energy a test charge would experience divided by the test charge itself. So we have a test charge in a field like this. Okay, it undergoes a change in potential energy. If we take that change in potential energy in joules divided by the test charge's charge in coulombs, that's equal to the change in the voltage that undergoes. Okay, so voltage is joules per coulomb. So we take if we have a voltage of 10 volts, that's 10 joules per coulomb. That means we stick a 1 coulomb of charge in. That coulomb of charge is going to have 10 joules of energy. Okay, units, volts equals V equals joules per coulomb, J over C. change in potential energy equals, basically we just solved this for potential energy. So change in potential energy is going to be equal to the test charge we stick in there, the positive test charge we stick in there, times delta V, the change in the voltage. And we get the same thing over again just as a reminder. But change in potential energy from up here, change in potential energy is equal to QED. So QED, so therefore the change in voltage equals QED divided by Q. Okay, see all these things are coming together here. The Q's cancel and we get ED. So change in voltage is equal to the electric field times the distance over which the charge is moved in that electric field. That's how much the voltage would have changed. So many times, okay, yeah. So now we introduce something called an electron volt here. Many times scientists have to deal with energies of submicroscopic particles, electrons, protons. They're very, very small numbers in joules, right? So maybe you don't like to work with those kind of numbers if you have to work with them a lot, even though very small energies like that can destroy molecules and do all sorts of impressive things. But in order to escape that, what we do is the following. So we know that the change in kinetic energy is equal to the minus the change in the potential energy. In other words, the decrease in potential energy is equal to the increase in kinetic energy. Okay, so but we know that potential energy, in this case the electron, times the change in the voltage. Okay, that's the where is it? So change in voltage ED. So so we have this. So then we put in the charge of the electron. We get the minus sign out front. The minus signs are going to go away. Times 1 volt would be plus 1.6 times 10 to the minus 19 joules. So in other words, these energies are extremely, so 1 electron volt is the energy required to accelerate a fundamental charge such as an electron, that's the 1.6 times 10 to the minus 19 coulombs, through a voltage difference of 1 volt. So the point is, how much energy does it take in joules to accelerate an electron, for example, through 1 volt? How much energy is required? And it would be 1.6 times 10 to the minus 19 joules. But if you don't want to keep writing 1.6 times 10 to the minus 19 joules, just call it 1 electron volt. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. Okay, so electric potential and a uniform electric field. So work is done by the electric field in moving a positive charge Q from positive plate A to negative plate B. So we're going to say this is a positive charge, and so the field does work on it, just like the gravitational force does a work on a mass. You hold a mass up in the air, you let it go, it falls to the earth. The gravitational field, through the gravitational force, is doing work on that mass. Here, we'd say we're hanging on to this Q here, this positive charge, we're holding it there, we're not letting it go. Then we let it go, what's it going to do? It's going to go whoosh, just like that. Just like the mass towards the ground, the Q is going to go, the charge is going to go away from the positive plate towards the negative plate. So the work, again, is from physics 5A, change in potential energy, that's equal to the charge times the change in the voltage. Remember, voltage is joules per coulomb. So joules is equal to coulombs times volts. So then we have the change in voltage is equal to minus VB minus VA. Remember, this is a VB over here. This is negative. So this is a higher voltage. VA is a larger voltage than VB because this is plus, this is minus. All right, so go through the minus sign. We got VA minus VB now. And then we're going to call that VAB, the voltage between these two plates. So the work equals QVAB. Okay, we just plugged it in up here. Minus delta V minus delta V is equal to VAB. So work now becomes QVAB. Work equals force times distance over which the force is applied. Well, force is equal to the charge times the electric field again. So I plug in what, so now here we've got the QVAB equals QED. Okay, because we're plugging in QE right here for the force, and we know that work is equal to QVAB. So in other words, this QVAB comes from up here. Okay, there. And so this over here, QED, that comes from plugging QE in for force up here. So these two are equal to each other. The Q's cancel. VAB equals the electric field times the distance over which the particles moved. And E equals VAB over D. So now we got another thing for the electric field. Before, it was newtons per coulomb. Now it's volts per meter, okay? But they're interchangeable. Okay, so now for a point charge, remember we had for the electric field way back in chapter 18, up here we had for electric field for a point charge, E equals KQ over R squared. So now we have KQ over R squared for a point charge. Well, V, now we're basically just D and R. They're both distances in meters. Okay, in this case, R is kind of a radius. That's why they're using R here. So, so V equals ER. You're used to seeing this as V equals ED. Okay, so that means that KQ R squared, this guy right here, times R. Oops, one of the R's canceled. So we got V equals KQ over R. So that's how you find out the voltage for a specific charge. So here's a charge Q. Okay, what is it? We don't know. Doesn't matter. This equation still works. K is just Coulomb's constant. The 8.99 or 9.00 times 10 to the 9th newtons meter squared per coulomb squared. And R is the distance out. So the only thing that's, once you set your charge there, your charge is set. That stays constant. K is a constant. Coulomb's constant. So the only thing that varies there is R. So in close, we should have a bigger voltage, but as R gets bigger and bigger, we get out here further and further, the voltage is going to go down. The voltage that exists out here. Okay, remember voltage is joules per coulomb, so we put a charge in here, it's going to have less and less energy as we get further and further away from Q. Okay. Okay, we're here. All right, equipotential surfaces. Now, if you take this guy here, remember to keep this equation in mind. The only thing that varies is R, okay? Well, you take these little circles here. These are the equipotential surfaces. And basically, R is the same all the way around the circle. So we would get the same voltage everywhere, right? Oops, didn't mean to do that. So you go back up here. Should I have it here? There, it's right there, so I don't have to keep going back up. All right, so R is the only thing that changes. But see here, R is the radius, so we got that far, we got R there, we got the same R here, same R here. So all the way around the circle here, we're going to have the same R, and that's the only thing that changes in here. The charge doesn't change, so we have the same voltage. So the same voltage all the way around it. That's called an equipotential surface. We go out to this guy, R is different, it's bigger, so the voltage is going to be smaller, but it'll be the same. Every time we plug it in, the same R there, we're going to get the same voltage up here. So up here we have the same voltage, another equipotential surface. Since V equals KQ over R for a given point charge, it follows that the voltages, the same distance R from the charge, would be equal. Okay, these are called equipotential surfaces. Electric field lines radiate out from the charge perpendicular to the equipotential surfaces. So you can see these guys are radiating out. These are the electric field lines. They're perpendicular to the equipotential equipotential surfaces. And here's some other examples. These are 2 point charges. If we're going to, remember, I think you guys watched it already. Where is it? This guy here. Remember, this is a lab we would have done if we were meeting in class. You would have put different voltages across there. That'd be 0 volts. That could be like 10 volts. You take a voltmeter and you measure the same voltage all the way across there, across there, across there, across there. You get your equipotential surfaces. Then you draw in your electric field lines, making sure they stay perpendicular to the equipotential surfaces. You got to kind of curve them around so they always hit. You got to imagine there's a billion, gazillion, infinite number of equipotential surfaces. So it's got to curve around to all those imaginary ones we didn't draw because we didn't have time. It's got to kind of meet all those and curve in and come in perpendicular here. Okay, so that's what that would look like. Okay, now here's a case where, see, these are the same charge. So they got minus 10 and minus 10. Well, the electric field lines aren't going to go from one to the other. Remember, the electric field lines start from the positive charge and end on the negative charge. So you got electric field lines that are all going to end on these guys. So what would happen is you get something like this. Okay, so you go around measuring. You probably get 5 volts here, and this is where you'd measure your 5 volts everywhere around. As you put your probe down and touch the paper, you measure minus 5 volts all the way here. Go out here and you kind of get a minus 2 volts kind of out here like this. So now if you draw in your electric field lines, you got electric field line coming off perpendicular. This is a equipotential surface as well. So the line's got to come off perpendicular. There it's a conductor. Remember, the electric field lines are perpendicular to that. It's got to come off. It's got to be perpendicular there. But now to be perpendicular to the next one, it's got to come around like this. It's got to curve back. Same thing over here. So they're going to curve like this. They're going to like not meet each other. Okay, so that's what two are the same. Now this is the one, this is the important one, because this is kind of like what the capacitor is built on. This is like a capacitor. We're not calling it a capacitor yet. Parallel plates. So you would have done this in the lab also. You would have had two, instead of like the circles drawn in, like this, you would have these two squares drawn in. And then you would have gone through, measured all the voltages. So in this case here, these are the equipotential surfaces. So this is all 100 volts, and this is an example. This is all 0 volts. I think this is right out of your textbook. We go along, we measure 75 volts, 75 volts, 75 volts, and we make little dots, and we connect them all, kind of, not connect the dots like straight lines, but curve around. Then we'd have 50 right down the middle, because we go from 0 to 100. We'd have 25 over here, okay, 0 to 100. So there would be, these would be the equipotential surfaces, the 100, the 75, the 50, the 25. There's 25 volts all the way down here. Then we draw from the plus to minus, we draw in the electric field lines, just like this. And right here in the middle, they're more closer together, so we have a stronger electric field in here than we would out here. All right, we can leave capacitors for next time. And this is what I want. Yeah, okay. So this is the worksheet. I didn't add anything to it. So everything's the same. It's due Tuesday, July 14th. And so we did these already. So here are the chapter 19 ones we haven't done yet. A bare helium nucleus has 2 positive charges and a mass of 6.64 times 10 to the minus 27 kilograms. Calculate the kinetic energy in joules at 2% the speed of light. Speed of light is 3 times 10 to the 8th meters per second. So to get 2% of that, we multiply it by 0.02. And they've got 3 significant digits, so we want to use 3 significant digits here as well. So 0.02, in other words, if it was 100% the speed of light, we put a 1 there. If it was 80% the speed of light, we put a 0.8 there. But it's only 2%, so we put a 0.02 there. So this will give us the velocity that it's traveling at. See there, it's the same a formula for the kinetic energy that you had in 5A, 1/2 mv squared. So we got the 1/2, we've got the mass right there, so you just multiply it out, and you end up with 1.195 times 10 to the minus 13 joules. But if we want to have 3 significant digits, we'd make it 1.20 times 10 to the minus 13 joules. So that would be the kinetic energy in joules of this mass, positive charges of this mass, okay? And then the next part says, what is this in electron volts? Okay, so that means we got to convert. See how small that number is? We want to mess around with minus 10 to the minus 13 joules all day? Or do we want to come here and see what it would be in electron volts? Where did I do that? Here's where we did it. Okay, so 1 electron volt turned out to be 1.6 times 10 to the minus 19 joules. Remember that 1 electron volt is the energy we would need to accelerate the fundamental charge, the 1.6 times 10 to the minus 19 coulombs, through a voltage of 1 volt. And if we plug it into this equation here, it turns out that it's 1.6 times 10 to the minus 19 joules. So we'll just call that 1 electron volt. Okay? So it's 1 electron volt. So here, oh, they're used, okay. We're back to the 1.1. I guess what you're supposed to do is you're supposed to use all the significant digits and then round it off at the end, I guess. So we used all the significant digits here times 10 to the minus 13. We got 1 electron volt per 1.6 times 10 to the minus 19 joules. So joules would cancel, we'll be left with electron volts. So this would be 7.47 times 10 to the 5th electron volts, more in the range of numbers we're kind of used to. And then what voltage would be needed to obtain this energy? Well, kinetic energy is like the potential energy. It's the decrease in potential energy is the increase in kinetic energy. So we've got the QV, or voltage is joules per coulomb. So the energy is going to be coulombs times volts. So there it is right there, because we got the kinetic energy we ended up with divided by the charge. We've got two positive charges. The helium, basically helium nucleus has two positive charges and a mass. So it's two protons. So we got to go 2 times 1.6 times 10 to the minus 19 coulombs for the charge down here. So basically it's just taking this over this, and we would need 3.73 times 10 to the 5th volts to accomplish that. Okay, then number 13 in your own on chapter 19. Show that units of volts per meter and newtons per coulomb for electric field strength are indeed equivalent. Well, remember, voltage is going to be joules per coulomb, energy per charge, okay? So if you said you had 10 volts, that means you'd have 10 joules of energy. If you put 1 coulomb of charge in your electric field, it would have 10 joules of energy if that's what you put in there. Now, so that means 1 joule equals 1 Newton meter. Well, that just comes from work equals force times distance, for example. Work equals force in newtons times distance, and of course work is in joules. So 1 volt per meter, okay, equals 1 joule per coulomb. So I'm plugging in for the volt. So the volt is 1 joule per coulomb. Joule per coulomb over here. We got the meter on the bottom, so the meter's down on the bottom with the coulomb. Okay, but joule is right here, Newton meters. So you got Newton meters here for the joule. The meters cancel. We get Newton per coulomb. So that's how we could show that 1 volt per meter is equal to 1 Newton per coulomb. So you can go back and forth on the units. Just remember, you're going to get some problems. It'll give you voltages and distances, but then it'll give you the electric field in newtons per coulomb. Just remember, but Newton per coulomb is the same as volt per meter, and vice versa. Okay. The field strength between two parallel conducting plates separated by 4.00 centimeters is 7.50 times 10 to the 4th volts per meter. What is the potential difference between the plates? Well, remember, we have the voltage between the plates is equal to the electric field times the distance between the plates for moving that charge from one plate to the other plate. Okay, so we're told the electric field, there it is right there, volts per meter. And then we're told the distance, 4 centimeters, is 0.04 meters. And we get 3 times 10 to the 3rd volts, or 3 kilovolts. That would be so what is the potential difference between the plates? It would be 3,000 volts, 3 kilovolts. Okay, the plate with the lowest potential is taken to be 0 volts, because all we're really interested in is differences in voltage. Okay, and then here's the word potential. I should have mentioned it. Potential difference and voltage mean the same thing. Okay, when you say potential difference, you say, we have 10 volts. You say, well, what's the potential difference? Well, the potential difference is 10 volts. What is the potential 1 centimeter from the plate and 3 centimeters from the other? Okay, so here it's the same deal. We've got the same electric field, but now we got a different distance. Instead of the whole 4 centimeters, now we only got 1 centimeter, so you plug that in. So if we were 1 centimeter from one plate, then we'd be up to 750 volts. So we started from 0, and then 1 centimeter away, we're at 750. Okay, 2 centimeters away, we'd be at 1,500. And then the whole 4 centimeters away, we'd be up to 3,000. See, it goes 750, 1,500, and then 2,025, and then 3,000. It'd go up every centimeter. It goes up 750 volts until we get 4 centimeters. It would be 3,000 volts. Will the electric field strength between parallel conducting plates exceed the breakdown strength for air? That means that's kind of like a lightning strike. We get it too strong of an electric field, the air breaks down. If the plates are separated by 2 millimeters and the potential difference is 5 times 10 to the third volts. Well, what do? We just figure out what electric field do we have. We have this voltage difference. We have this distance between the plates. Well, we got the electric field equals VAB, the voltage between those two plates, divided by the distance between them. Okay, so you got your 5,000 volts, 5 kilovolts, 5 times 10 to the third volts, divided by the 2 millimeters, 2 times 10 to the minus 3 meters. We get 2.5 times 10 to the 6 volts per meter, which is less than 3 times 10 to the 6 volts per meter. So no, the field strength is smaller than the breakdown strength for air. So it would not break down in that case. The air would not turn into a conductor because the electric field is so large. Then B, how close together can the plates be with this applied voltage? Okay, so we want to avoid this right here. This is the number we want to avoid, otherwise it'll break down. So we solve for D. Okay, so we got the same voltage here, and we're saying we don't want this. So if we make the plates too close together, okay, we'll get that breakdown. It'll break down. The field will be enough to cause it to break down. So anyway, if we put the two plates at 1.7 millimeters, okay, so remember right now there are 2 millimeters. If we put them closer together at 1.7 millimeters, then we would reach the 3 times 10 to the 6 voltage per meter, and we'd have it break down on us. How many more is there? Okay, an electron is to be accelerated in a uniform electric field having a strength of 2 times 10 to the 6 volts per meter. What energy in kilo electron volts is given to the electron if it is accelerated through 4.00 meters? Over what distance would it have to be accelerated to increase its energy by 50 giga electron volts? Okay, now remember, electron volts is 1.6 times 10 to the minus 19 joules, so it's even giga. Like giga means 10 to the mega is 10 to the 6th. I think giga is 10 to the 9th. Okay, but even there, it's not a big number at all. So again, we go back to the change in kinetic energy. So remember, the change in potential minus change in potential energy equals the change in kinetic energy. The decrease in potential energy is equal to the increase in the kinetic energy, equals the charge times the change in the voltage. Okay, well, we've got that the volts between the two plates AB is equal to the electric field times D. So that change in the kinetic energy equals QVAB equals QED. Okay, we just plugged in ED for VAB. Okay, so now we've got everything. We've got the electron. So we know the electron we already know is 1 point, and they dropped the minus sign, but 1.6 times 10 to the minus 19 coulombs. We know that the electric field is 2.00 times 10 to the 6 volts per meter. Then the distance between the plates is 2 meters. Now when we do all this, we do this part, we will have the energy in joules. Okay, so what we want to do first is convert over to electron volts. This will convert over to electron volts, but we want kilo. Did it ask for kilo? Oh yeah, it did ask for kilo electron volts. That's why I put kilo. Okay, so kilo electron volts. So then when we get this, we will have it in electron volts, but they asked for kilo, 1,000 electron volts, 10 to the third electron volts. So it ended up being 800 times 10 to the third, or kilo electron volts. Kilometer, kilogram. Okay, what does B ask for? Over what distance would it have to be accelerated to increase its energy by 50 giga electron volts? Okay, so the distance is equal to the change in kinetic energy over QE. Okay, so in this case, 50 times 10 to the 9th electron volts. Okay. The charge is 1.6 times 10 to the minus 19 coulombs. It's still talking electrons here. And the electric field is still 2 times 10 to the 6 volts per meter. Volts somehow got lowercase there. Don't know why. Okay, so we're just using this. And then we're converting it back into joules. Okay, so when you get this, you've got electron volts here. So you're going to have this number with electron volts in it. We don't want it to have electron volts in it. We want to get rid of the electron volts part, put it back into joules. So that's what this is for. So we would get the distance is 2.50 times 10 to the 4th meters, or 25 kilometers. So that's the distance it would have to be accelerated to increase its energy to 50 giga electron volts. And there's one more. Okay. Oh, this one's easy. What is the potential? 5.30 times 10 to the 10 meters. Okay, what is the potential? 0.530 times 10 to the minus 10 meters from a proton. The average distance between a proton, an electron, and a hydrogen atom. Okay, well, we just pull out this equation we had for the voltage, for the point charge. Remember, this is a point charge. So we've got the K, Coulomb's constant. We got the charge for the proton. We got the distance from the proton, and it would be 27.2 volts. Okay, so I think this takes care of everything in chapter 9 up until we get into capacitors, and I'll do capacitors later. I'll try to get the capacitor video up maybe by Tuesday. Okay, so I just have a little bit more work to do. So now this is a new PowerPoint, chapter 19. Oh, I may not have uploaded it to, where am I on this? Too many classes. Oh, this has got to be done by now. Please be done. It's finished. Good. This shouldn't take long. Let's see why it didn't take long at all. Okay. No, I haven't uploaded 19. It will be before I email you about this video and everything. I'll have the PowerPoint for 19 up. Remember, I'm not finished. We're not finished with chapter 19. So even though there's more stuff here, I go into the capacitors and stuff. So we didn't do this. we stopped here. So we didn't do this guy, this stuff, and this. And I got more to add too. So that'll get added. And so this is if you download this tomorrow, remember that this one isn't finished. You gotta I have to upload it and say yes, I want to replace 19.5 that's already there. Okay, so I think that's everything. I've been on here for a while now, and it's probably going to take all night into tomorrow to upload this thing, so I better quit now. So I'll say good night for now, and I'll talk to you later.